In every engine, from the one in your car to the massive turbines chugging away in a power plant, there's this invisible speed limit. It's a hard ceiling on efficiency that no amount of clever engineering can ever break. Today, we're going to break down the beautiful, elegant idea that actually defines this limit, the Carnot cycle, basically the blueprint for a perfect engine.
So let's just start with a big question. If you have a source of heat, like burning fuel, what is the absolute most you can possibly get out of it in terms of useful work? Is it 50%? 80%? Is it even possible to get to 100%? And this isn't just some abstract engineering problem, right? This gets to the very heart of the laws of physics.
Well, the person who first cracked this code was a brilliant French engineer named Sadi Carnot. Way back in 1824, he just imagined an ideal engine. His concept was stunningly simple. You've got a hot source at some temperature T1, a cold sink at a temperature T2, and this perfect little engine working between them. And the key to the whole thing was that his engine was perfectly reversible, which is just a fancy way of saying no energy gets wasted on stuff like friction.
To really explain how this perfect engine works, Carnot laid out this four-step process. This whole journey, which we now call the Carnot cycle, is a complete closed loop for a substance like an ideal gas. And you can map it all out on a pressure-volume graph.
And here is that map. This is the famous pressure-volume diagram, or PV diagram, for the Carnot cycle. Now, I know it looks a little complicated, but all it's doing is tracking the state of the gas inside our engine. The up and down axis is pressure, and the side-to-side axis is volume. This closed loop, going from point 1 to 2 to 3 to 4 and right back to the start, that represents one full cycle where the engine sucks in heat and spits out useful work. So let's break that journey down.
All right, the really important part is how it does that. So let's follow the gas step by step and see exactly how that heat gets turned into work.
Okay, we're starting at point 1. The engine is touching the hot source. It's absorbing heat, which we'll call Q1. And that energy makes the gas inside expand, which pushes on a piston and does some work. The key word here is isothermal. It just means this whole process happens at a constant high temperature T1. All that heat energy it just absorbed goes directly into the work of expansion. Simple as that. Next up, step 2. We completely insulate the engine. No heat can get in or out now. We call this adiabatic. The gas, it keeps expanding, it keeps doing work, but now it has to pay for it by using its own internal energy. And because it's spending its own energy, its temperature takes a nosedive, dropping all the way from the high T1 down to the cold temperature T2.
All right, for step 3, we have to start resetting the whole system. We put the engine in contact with the cold sink and we start to compress the gas. So now, work is being done on the gas. To stop it from heating up, the engine has to dump some waste heat, we'll call that Q2, into the cold environment. And this all happens at that constant low temperature T2. This is a really critical step. You absolutely have to get rid of some heat to finish the cycle.
And finally, we insulate the engine one more time for this last adiabatic step. We keep compressing the gas, doing more work on it, but now, with nowhere for that energy to go, the internal energy and the temperature of the gas shoots right back up, taking it all the way from T2 back to our starting temperature T1 at point 1. The engine is now exactly where it started, totally reset and ready to go through the cycle all over again. So that's the whole four-step dance. But you know what? The real magic here isn't in the mechanics, it's in the math. What looks kind of complicated on the surface actually boils down to an equation that is just shockingly simple. Let's see how that happens.
Okay, to find the total work the engine does, we add up the work from the 2 expansion steps, and then we subtract the work it took to do the 2 compression steps. And here is the first really cool simplification. It turns out that the work done during the adiabatic expansion is perfectly canceled out by the work done on the gas during the adiabatic compression. They're equal and opposite, so poof, they just disappear from our equation.
Now the final piece of the puzzle, the little secret that unlocks everything, comes from the physics of those 2 adiabatic steps. For an ideal gas, there's this relationship that says temperature times volume raised to a power stays constant. When you apply this to our 2 adiabatic steps, and then divide the equations, you get this perfect symmetry. The ratio of the volumes during the expansion is exactly the same as the ratio during the compression. And this is the moment. This is where it all clicks into place. Because those volume ratios are identical, the messy-looking logarithm parts of our work equation just completely cancel each other out. And all of a sudden, the efficiency, that's the net work you get out divided by the heat you put in, it all collapses down into this incredibly beautiful formula. The maximum possible efficiency of any heat engine is just 1 minus the cold temperature divided by the hot temperature. That's it. The materials don't matter, the size of the engine doesn't matter, it all just comes down to the temperatures.
So why is this one simple formula so unbelievably important? Well, it's not just a neat piece of math. It has huge real-world consequences, which are all summed up in what we now call Carnot's theorem.
This theorem gives us 3 unbreakable rules. First, it doesn't matter what you make your engine out of. The limit is universal, whether you're using steam, air, whatever. Second, it's a theoretical ceiling. No real engine, with all its friction and imperfections, can ever be more efficient than a perfect Carnot engine running between the same 2 temperatures. It is the ultimate speed limit. And third, the cold, hard limit of reality. For the formula to give you 100% efficiency, the cold sink, T2, would have to be absolute zero. And since we can't physically reach absolute zero, perfect efficiency is impossible. Period.
So that leaves us with this final thought. A formula that was thought up almost 200 years ago still sets the absolute physical limits on everything from our power plants to our cars. It tells us that efficiency is really just a game of temperature differences, and that some energy is always going to be lost as waste heat. So the question for us is, how do we get creative and innovate within these fundamental limits to build a more efficient, more sustainable energy future?